Hello students, so this is lecture 5 on quantum harmonic oscillator, and in this lecture also we will continue our discussion from the last lecture. So in the last lecture we have derived two important relations. The first was when the A dagger, which is your raising operator, operates on n, it will give you under root of n plus 1 into ket of n plus 1. So you can see that the index of n has been raised by a factor of 1, and when a operates on n, you will get under root of n into ket n minus 1. Okay, so here you can see that the index of n has been reduced by 1. So here it has been increased by 1 and here it has been reduced by 1. So that's why this is known as raising operator, and this is known as lowering operator. So these are the two important relations which we have derived in the last lecture. So now we will continue our discussion with this. So what will happen when the combination of A dagger and the A operator will operate on a state n? So if A dagger A operates on a state n, then what we will get? So first of all, we will keep A dagger outside and we will operate state A with n. So this is equal to A dagger into, so when A operates on ket n, it will be under root of n into ket of n minus 1. Okay, so now I can take under root of n outside and I can operate A dagger with ket n minus 1. So when A dagger operates on ket of n minus 1, you will get under root of n minus 1 plus 1, and here you will get n minus 1 plus 1. Okay, so this is root n into root n, and here you will get n. So when A dagger A operates on a state n, you will get n into ket n. Okay, so you can see that you are getting here, okay, the state itself, the label of the state itself. So if you operate on an unidentified state, okay, if this value of n is not known to you, then you can operate A dagger A operate on state n, and you will get this value of n, okay, here. So you can easily identify that on which state your measurement is done. Okay, so this combination of A dagger A is generally known as number operator, okay, and denoted by capital N operator. Okay, so combination of two operator is also an operator. Okay, and so A dagger A is number operator, and the more concise way of writing this is when the number operator operates on state n, you will get this thing. Okay, so this is an important relation. Okay, so now let us move forward and think about that what will happen when the Hamiltonian operator operates on n. Okay, so from your previous class we know that Hamiltonian operator in the A dagger A operator formalism can be written as h cut omega into A dagger A plus 1 by 2, okay, into ket of n. So this is h cut omega, and this A dagger A is nothing but the number operator operating on n plus 1 by 2 and into n. Since 1 by 2 is not an operator, it's just a constant, so it will have no action on the state n. So this will be h cut omega n operating on capital N. Number operator operating on n will give you small n plus 1 by 2, okay, into this. So this can be written as h cut omega into n plus 1 by 2 into ket n. So okay, so this is another important relation. Now we all know that when the Hamiltonian operator operates on a state, then the eigenvalue is nothing but energy. So these are your energy eigenvalues. Okay, not all eigenvalues are energy eigenvalues. Only energy eigenvalues will be given to you when the Hamiltonian operator operates on a state n into state n. Okay, so if I compare this equation and this equation, then you can easily see that En is equal to h cut omega into n plus 1 by 2. Okay, so this is the expression for energy eigenvalues which we have derived. Now this is not a new equation for you. We have derived this expression of energy eigenvalues in the first class also. Okay, but in that class we have used the Schrodinger's approach, okay, of solving quantum mechanical systems. So in that we have not introduced those operator methods and all those things, and it was a quite a cumbersome method. You have to use differential equations, you have to find the solutions of differential equations, you have to approximate some things and all those things, and then you find this energy eigenvalues. But here you can see that you have not done anything. You have just introduced two operators, and in the four steps itself it is giving you the energy eigenvalues. So this is the advantage of operator algebra in quantum mechanics, and this is a modern technique of doing quantum mechanics, and now most of the quantum mechanics is done using operator algebra. Okay, so let us continue our discussion with this. So I will derive two important commutation relations involving the number operator. So what will happen if you are having n comma a? Okay, so a dagger a comma a. So this can be written as a dagger into a comma a plus a dagger comma a into a. So a with a will be 0. Now you have this term, so you know that a comma a dagger is equal to 1. So a dagger comma a will be minus 1. So now you can write that the number operator with a operator will give you minus of a. So this is another important result. Okay. And similarly you can also derive the commutation relation of n with a dagger. Here you will get positive of a dagger. Okay. So these are the two important relations. And now how to represent a wave function. So now I will discuss about representation of a state. Okay, so representation of state, I am talking context of only this system, which is a quantum harmonic oscillator. So you know when a dagger, okay, operates on state 0, you will get under root of n into cat 1. Okay, so I can write cat 1, okay, is equal to a dagger operating on 0 divided by root 1. Okay, now when a dagger operates on 1, it will give you root 2 into cat 2. So I can again write cat 2 is equal to a dagger into 1 divided by root 2. Okay, so if I use this value of cat 1 in this expression, then what I will get? So I can write cat 2 is equal to a dagger into, instead of writing cat 1, I will write a dagger operating on 0 divided by, so here I am having root 2 and root 1 from this equation. So this can be written as, okay, so again if I want to write cat 3, then you can follow the same pattern. You have to write a dagger into a dagger into a dagger operating on 0. Okay, so you can see that what will happen. So here we are having 0, so a dagger will increase the value of 0 by 1, so you will get cat 1. When now this will operate, so this will make 2, and when this will act, then it will make it 3, and you have to divide it by root 3 into root 2 into root 1. You have to just follow the same fashion. So similarly, I can write for nth state a dagger raised to n into cat 0 divided by under root of n factorial. Okay, so this is also a very important expression in quantum harmonic oscillator algebra. Okay, that cat n is equal to a dagger raised to n cat 0 divided by root of n factorial. Okay, now, so this was how you can represent any state. Okay, if you want to represent third excited state or fourth excited state, anything you want to represent, you can represent using a dagger operator, and you should only have the knowledge of the ground state. Okay, so now let us continue with something else. So we have derived, we have defined m omega by a operator is equal to m omega by 2h cross the position operator plus I, which is the iota, the complex iota, into m omega, and we have also defined a dagger, okay, which is equal to m omega by 2h cross x minus ip by m omega. So you can see that I have written this a operator, the lowering operator in terms of the position operator and the momentum operator, and here I have the definition of a dagger in terms of again position operator and the momentum operator. So I can use these two equations. Let me again write them as equation number 1 and 2, and using the equation number 1 and 2, I can write x and p. So x I can write and p in terms of, okay, a and a dagger. Okay, so what you have to do, you have to just add it and you have to once subtract it, so you will get the value of x and you will get the value of p. So you can check that you will get the value of x operator, the position operator, is equal to under root of h cross by 2m omega a plus a dagger, and you will get the definition of momentum operator is equal to I into m omega h cross by 2 into a dagger minus a. Okay. So these are the two definitions of position operator and this is your momentum operator. Okay, so you can do now a lot of interesting things using this definitions of position operator and momentum operator. Okay, so what we will do is we will find the expectation value of x. Okay, so I want to find the expectation value of position operator. Now if this would be the Schrodinger's way of doing quantum mechanics, then what you would be doing is you would be using psi star. Okay, then x psi to dx. Okay, and minus infinity to infinity. Okay, similarly you would be doing it for the expectation value of p. But in bracket algebra, you have to write the expectation value of x. In suppose you want to find, okay, expectation value of in the state n, so you will be writing bra n x operator into ket n. Okay, and now you have the definition of x operator here, okay, which is under root of h cross by 2m omega into a plus a dagger. So under root of h cross by 2m omega, and here I can write n and a plus a dagger into ket n. Okay, so this will be under root of h cross by 2m omega plus n into a dagger of n. Okay, so this is equal to, now when a will operate on n, so you will get, okay, some constant. So let me write it outside. Okay, so your constant will be under root of n, okay, and into n into ket of n minus 1. Okay, and here what you will get, under root of n plus 1 into n plus 1. So this is the thing which we have. And now you know that there is something like orthonormality relations. Okay, or conditions. Okay, so what orthonormality condition says, that a state has to be normalized, and it should be orthogonal. Yeah, so this is basically inner product. So n into n minus 1 is nothing but psi n star into psi of n minus 1. Okay, tx. And from your knowledge of Schrodinger's mechanics, you know that this is always 0 because two states are always orthogonal. Okay, and this again will be equal to 0. Okay, because the states are orthogonal. Okay. So you are left with under root of h cross by 2m omega. The first term is 0 and the second term is also 0. So the expectation value of x in any state, okay, is always equal to 0. Okay, so the expectation value of position operator, okay, for simple harmonic oscillator is always 0. Now you can in the similar way find the expectation value of p in any state, and this will also be equal to 0. Okay, so this I give you as an exercise. Just find it whether the expectation value of p is coming equal to 0 or not. Okay, you will get the same thing using the Schrodinger's mechanics also. Okay, if you are not using the operator method. Okay, so So these are the two important, very important results of simple harmonic oscillator problem in quantum mechanics. Okay. So suppose that if I want to find x square, then what I will do? Okay. So again, this is the expectation value of x square. So n into x square into n. So here again you have to take now since it is x square, so h cross by 2m omega will come outside, and here you are left with x n, and so these are two operators. Okay, so you can't take a direct square, you have to write it a plus a dagger into a plus a dagger. Okay, into cat of n. Okay, so this will be equal to h cross by 2m omega cat n, and here what you have to do is you have to first you will get a term called a into a plus a into a dagger plus a dagger into a plus a dagger into a dagger. Okay, into cat of n. Okay, so you will have to now solve four things. The first will be n into a into a into n, then n into a dagger into n. Okay, then n into a dagger a into n, sorry, and n into a dagger into a dagger into n. Okay, now see this term. Okay, what it will do, this will lower the state of n, so it will make this will make it n minus 1, and again when this will operate it will make it n minus 2, so n into n minus 2, this term is 0. Okay, here what will happen, here you are having n, so when a dagger will operate on n it will give you the state n plus 1. Again a dagger will operate on this n, so you will get n plus 2, and n into n plus 2, this will again be 0, but these two terms will not be equal to 0. Okay, so you have to calculate these two terms. Okay, and once you calculate these two values and substitute here, you will get the expectation value of x square operator equal to h cross by 2m omega into 2n plus 1. Okay, and similarly you have to find the expectation value of p square operator in the nth state, and you will get m omega h cross by 2 into 2n plus 1. Okay, so these are also two very important results. Okay, now okay, let us come to the uncertainty product. Okay, uncertainty product is the fundamental building block of quantum mechanics. Okay, so you must be knowing that uncertainty product is basically given with delta x into delta p. Okay, and it is generally always equal greater than or equal to h cross by 2. Okay, so this is something which the uncertainty relation in quantum mechanics says. So let us calculate the uncertainty product for ground state. Okay, so this delta x, okay, basically the uncertainty in the position. Okay, is generally given as under root of x square minus, okay, somewhat like the standard deviation formula. Okay, and if I calculate this thing for ground state, then what will be my value of 0 x square 0? So as I know that x square is equal to this thing, okay, so for ground state I will keep n equal to 0, so I will get h cross by 2m omega from this relation. So this is equal to h cross by 2m omega, and as we know that for any state this is equal to 0, so the square of this thing will be also equal to 0. So this delta x, if I write in terms of square only, then it is equal to, okay, h cross by 2m omega. Okay, and similarly if I find the uncertainty in the momentum, then this will be equal to under root of, okay, p square minus t square. Okay. So this, if I want to calculate, then for n is equal to 0, this quantity will be equal to m omega h cross by 2. Okay, and as we know that this value is 0 for any state, so the square will also be 0. So I can write now that delta p square is equal to m omega h cross by 2. So I can calculate the uncertainty product now, and this is equal to delta x square, okay, into delta p square is equal to h cross by 2m omega into m omega h cross by 2. So this will be equal to h cross square by 4. Okay, so if I write in terms of if I take the square, then I will get delta x into delta p is equal to h cross by 2. So you can see that this is the equality condition. So for ground state, okay, so this is the uncertainty product for ground state, and you can see that the uncertainty is minimum. Okay, so this is an important relation which we have got. Okay, and you can see that what the theorem says is proved here. Okay, so now the last thing of this lecture. Okay, see, you know that the energy eigenvalues of quantum harmonic oscillators are given as En is equal to h cross omega, okay, to n plus 1 by 2. Okay, so if I calculate E0, then you will get h cross omega by 2. This is known as 0 point energy. Okay, now you cannot find anything like this in uh, classical mechanics. So there is no analogous of 0 point energy in classical mechanics. In classical mechanics, the ground state energy is always equal to 0. But in quantum mechanics, the ground state energy is not equal to 0. So what is the origin of this 0 point energy? Why there is 0 point energy in quantum mechanics. Okay, not only for a simple harmonic oscillator, but you will find the same thing for any other system also. If you take the example of a potential well or any other kind of thing, you will always find there is a minimum finite 0 point energy. So what is the reason for that? Okay, so minimum non-zero 0 point energy. So what is the reason for this? So the origin of 0 point energy, okay, is fundamentally related with the Heisenberg's uncertainty relation. Okay, so how this comes, let us see. Okay, so let us find that how it is related with this thing. So we know that delta x square is equal to x square minus x square. So since this term is always equal to 0 for any state, so I can write this is equal to x square. Okay, and similarly I can write delta p square is equal to the expectation value of p square. Okay, so I am assuming that you know that these are all operators. So if I want to find, so you know that the total energy is equal to p square by 2m plus half kx square. So if I find the expectation value of this expression, then in the RHS I have to find the expectation value of p square operator by 2m plus half into k is a constant, and I have to find the expectation value of x square operator also. So now, so the expectation value of E, which is the average energy also, so you can write this as equal to delta P square by 2m plus half k into delta x square. So since we know that for ground state, or you can generally write that delta x square into delta p square is equal to h cross by 2. So you can write delta p square is equal to h cross by 2 into delta x square. Okay, so if I substitute this value of delta p square in this expression, then I will get h cross square. Okay, if I am not using this notation of ground state energy, then I will write, okay, delta x into delta p is always greater than equal to 0, and delta p is always greater than or equal to this. So I can write here then greater than or equal to sign by, so 2 is multiplied here and you will get, okay, so this is equal to, okay, so yeah, here I have to write 4, so here it will be 4. So 4 into 2, so this will be 8 into m into delta x square plus half into k into delta x square. Okay, so this is the value of this thing. Now for RHS to be minimum, Okay, since we are fighting the 0 point energy. Okay, see here in the whole derivation, the heart of the derivation is this thing. Okay, which is the Heisenberg's uncertainty principle. So for RHS to be minimum, you can differentiate. Okay, differentiating E with respect to delta x square. Okay, so if you do this, okay, and for minimizing the differentiation of delta E with delta x square, okay, should be equal to 0. Okay, for minima. Okay, this is a general condition for minima. We are actually minimizing E with respect to delta x square. Okay, so you will get, okay, so this term will be equal to 0 and equal to h cut square by 8m into delta x, okay, raised to 4 minima plus half into k equal to, okay, sorry, I have written 0 here. So if you write this, then you will get the value of delta x corresponding to minima equal to h cut square by 2m omega. Okay, so you can substitute this value of delta x minima in your expression of this thing, okay, in this equation. Okay, so how this equation will be written for E minima? E minimum is equal to h cut square by 8m into delta x square minimum plus half into k into delta x square minimum. Okay, so I have to substitute the value of delta x square minimum at both of these things. So this will be then your E minima will be equal to h cut square by 8m into 2m omega by h cut square plus half m omega square into h cross by 2m omega, and this value will give you, sorry, here it is only h, just a minute, here you will get only h cut. Okay, so you will calculate that your minimum energy using Heisenberg's uncertainty relation will be half h cut omega, and this is nothing but the 0 point energy. Okay, so you can explain the origin of 0 point energy using Heisenberg's uncertainty relation. This is what this derivation says about. Okay.